Okay. So if we happen to get one of these exact values, so if our test statistic, our sum turned out to be 40 exactly, the amount in our tail area would be 0.189, or if it was 46 exactly, it would be whatever number corresponds to 46, 0.041, etc., etc. Okay? But in our circumstance, we didn't get one of those exact numbers. We got 49.5. So the numbers, 49.5 is between 48 and 50. 48 is 0.021, and 50 is 0.0093. Okay, so I just write 0.021 here and 0.0093. So 49.5, the corresponding tail area will be between 0.021 and 0.0093. Is that okay with you guys? Okay. I erased it, but I think I said we're using the directional alternative, right? Okay, I said we'll use directional. Okay, so we said, and the directional alternative was that the growth section tends to be larger, tends to produce values, or I'll just write informally, be larger than the gap section. Gap section values. So we've gone through and we found the tail area, but we have to remember to do our directionality check. Okay? And the directionality check is simple. If the growth section values tend to be larger than the gap section values, then the sum from the growth section needs to be larger than the sum from the gap section. And that's the case. Okay? The sum from the growth section is 49.5. Sum from the gap section is 6.5. So for our directionality check, passes. Okay, sum for growth is indeed that larger than the sum for gap. And so how does our p-value work? Okay, so this is where things get a little bit weird. Or not weird, but you just have to read this table here, okay? And it reminds you whether these values are for a non-directional or a directional test, okay? So at the very top, it says, this table provides selected values of the test statistic in bold type and corresponding p-values for a non-directional alternative in italics. Directional p-values are found by dividing the numbers in italics in half. So we have a directional alternative. So our tail area is between 0.0093 and 0.021 based on our test statistic 49.5. But that's for a non-directional one, so if we want a directional p-value, we have to take this and divide by 2. So our p-value is going to be less than 0.021 divided by 2, and that becomes 0.0105. And this we divide by 2, and we get 0.00465. Yes?
This is defined a p-value for a non-directional test?
For a directional one. Okay. So the table says the values these values, 0.021 and 0.0093, the ones that you find in the table correspond to a non-directional test. If you want a directional test, you take these values and you divide by 2, assuming it passes the directionality check. Right? So if it didn't pass the directionality check, we would just stop and say, we don't have evidence to support the alternative. But it passed the directionality check, so we take our tail areas and we divide by 2, and that gives us our p-values. Yeah.
Sorry, can you do that one more time? So for the in the table, that's for a directional test, and then the p-values...
In the table, it's for a non-directional test. And if you want a directional one, you take them and divide by 2. It says in the table itself, okay? So when you use this, it's just a good idea just to read the top paragraph at the top, and you're like, oh yes. It tells you very clearly, it says directional p-values are found by dividing the numbers in italics in half. So you just say, oh, is this directional? Yes, I'm going to divide these in half. Is it non-directional? Then I just use these. Okay, and so we go through the process, and we get this p-value. And so what does our p-value tell us to do? Okay, so if our significance level, let's just assume we're using alpha is equal to 0.05. Our p-value is smaller than alpha, and so we would reject the null hypothesis. And so we have evidence to support the alternative, which says we have evidence to say the values from the growth section tend to be larger than the values from the gap section, okay? Or the distribution corresponding to the growth section tend to produce values that are larger than the distribution corresponding to the gap section, or whatever I had written in the alternative hypothesis in the game.
Directionality check. Can you go over that one more time, please?
So, directionality check basically says that your data needs to at least be in the same direction as your alternative. So my alternative said that the numbers from the growth section tend to be larger than the numbers from the gap section. Okay? So to check that, well, I mean, I can look at the numbers and say, oh yeah, they tend to be larger. But the formal check is you take the sum from the growth section and you take the sum from the gap section. And because this said the growth would be larger than the gap, the sum from the growth needs to be larger than the sum from the gap. Is that the case? Yes. So it passes our directionality check. Now if my alternative said the gap values tend to be larger than the growth values, when I look at the sums, I would see that the gap sum is smaller than the growth sum. So then it would not pass the directionality check if I had written the flip side as our alternative. Okay. Is that all right? Okay, so that is it for the Wilcoxon-Mann-Whitney test. Okay, you are responsible for knowing that. It will make an appearance on your final exam. And again, no symbols in our hypotheses there. It's written out in this kind of wordy fashion. And we're not using mu. We're not doing any of those types of things. And again, this is just one example of a test in this class of non-parametric tests. So non-parametric, we're not putting any kind of assumptions on the thing. And there's lots of tests in the entire field of statistics, but this is just our exposure to non-parametric statistics. Last week, I covered briefly one section from Chapter 8, or two sections from Chapter 8, which is on the paired t-test. Okay? The rest of Chapter 8 is on more paired data tests. Okay? And a lot of those tests are actually non-parametric tests. So they list off a lot of non-parametric tests for paired data. Okay? You are not responsible for learning those, but if ever in your future you encounter a situation where you feel like this is paired data and it's non-parametric, you know where to look in your book to get an idea of what to do. Okay. So chapter 8 does a lot of other paired tests, parametric and non-parametric. Okay, we are going to move on to chapters 9 and 10. It feels like a lot, but it's not, okay? So we are shifting the types of data that we are going to encounter. So chapter 7, the t-test, and this Wilcoxon-Mann test, we were dealing with numeric data. Okay, so when you're trying to compare samples of data that's numeric data, we would do the t-test or Wilcoxon-Mann test or a paired t-test. With chapters 9 and 10, we are not looking at numeric data, we are looking at categorical data. Okay. We'll do inference. So now, when we take samples of data, we're not asking what is the mean of the sample, we're going to ask what proportion of the sample has this property, okay? So it could be, you know, you take a sample of people, what proportion is female? Or what proportion of these people have black hair? Or if we're talking about cars, it could be what proportion of cars have 4 doors? Or what proportion of cars, you know, have a, I don't know, 4-cylinder engine? Things like that, okay? We're looking at categorical data, and the statistic from our sample is the sample proportion. Okay? So in a sample, we will have count of, quote, successes, or whatever property we are looking at. The sample size n, and the sample proportion. P hat, which is equal to y over n. Simple enough. So we can create a confidence interval for P. So again, the idea behind a confidence interval is based on what we see in a sample, we're trying to infer something about the population. So if we observe a sample with some proportion P hat, what does that tell us about the proportion that exists in the population? So we can make confidence intervals about the population proportion P based on our sample. And so we would say something like, I am 95% confident that the proportion of whatever it is, vehicles that have 4 doors is between 75% and 90%, or something like that. Who knows? There.
Is the population proportion P different from P hat?
Yeah, so p hat is your sample proportion. That's something we can observe. P is the proportion in the population which we cannot observe directly. So what we're doing is, based on what we see in our sample, we want to make our best guess or best interval about the proportion P in the population. Okay. So when we're dealing with numeric variables, we could not observe the mean of the population directly. That was mu. We could not observe that directly. But we could observe a sample with sample mean y bar. Based on that sample mean, what does it say about the population mean? Same idea here. We're observing a sample. We get a proportion in our sample. And based on that, what does it say about the population proportion P? Okay. Okay, so I have to say our book does something unusual, and it's not wrong, and I understand why they're doing this. But in terms of other statistics textbooks, this is the only text that I've seen do confidence intervals this way. So I just want to maybe talk about maybe the more common way, but you will not be responsible for learning it. Okay, so most other texts base their confidence intervals for P based directly on their sample proportion P. Oh, sorry. So most other texts will use P hat as the basis for their confidence interval for P. Okay. Our text uses an adjusted sample proportion. Okay. Sample proportion. Okay. And so it's called the Wilson's adjusted sample proportion, and the symbol they use is P tilde, P squiggle, as the adjusted sample proportion. And so this, what they do is they take the count and you add 2, and you take your sample size and you add 4. Okay. And the reason for this is to avoid extreme values near 0 or 1. Okay. So, for example, let's say you wanted to know what is the percentage of people with some rare disease. Okay. What percentage of So some rare disease, let's say you want to figure out the percentage. So maybe you go out and you survey 200 people. Okay. You survey 200 people, and maybe you find 0 cases of this rare disease. So your sample proportion, your p hat, is 0. And our formulas fall apart when you find a proportion of 0. Okay. okay, because then it turns out your standard error is 0, and then you have no confidence interval there, okay? So what this does is it says, okay, so if you observed 200 people and you found 0, we're going to pretend that you looked at 4 more people where 2 of them were successes and 2 were not, basically. Okay? So it kind of sticks in some numbers there so you don't get a proportion of 0. Okay, so now you have 2 out of 204, so you have a very small percentage, less than 1%, or about 1%, but it's not 0. And then the flip side is also true. Okay? Maybe you want to know, what percentage of people have 5 fingers on their left hand. And maybe you survey 100 people. And all 100 people that you asked maybe have 5 fingers. Okay? And then so in that case, your sample proportion is 100%. And again, things fall apart when they're at 100%. So the adjusted sample proportion says you looked at 4 more people and only 2 of them had that thing. So now you have 102 cases out of 104. So you have something like 99%. So this basically forces your sample proportion away from 0 and 1. Okay? So the adjusted sample proportion moves us away from 0 or 1. Okay? When it's close to the middle, it doesn't really make a difference. But this is what we use for our adjusted sample proportion, p tilde. And so your confidence interval, and we're only going to learn the 95% confidence interval. And because if you choose a different something other than 95% confidence interval, you have to change these numbers from 2 and 4 to different numbers. So we're just going to leave it like this. And so the 95% confidence interval is p tilde plus or minus 1.96 times the standard error, which is plus 4, okay? So, for an example, let's say we want to know what is this? Okay. So here's an example. It says, as part of the National Survey of Family Growth, 496 women aged 20 to 24 who had given birth were asked about their smoking habits. Smoking during pregnancy was reported by 78 of those sampled, which is 15.7%. Okay, so let's make a 95% confidence interval. Okay, so we surveyed 496 people. So these numbers are actually chosen to make our life a little easier. Surveyed 496 women who had recently given birth. '78 reported smoking during pregnancy. So we will make a 95% confidence interval. 95% confidence interval for the proportion in the population California, we generally have fewer people smoking than the rest of the country. But okay, so our P tilde, our adjusted sample proportion, would be 78 plus 2 over 496 plus 4, so I get 80 over 500, at 16%. Our confidence interval is P tilde plus or minus 1.96 times the square root so 0.16 plus or minus 1.96 times something. So 0.16 plus or minus 0.032. So that gives me 0.192 and 0.028. I'm sorry, 0.128. So I would say I have 95% confidence that between 12.8% and 19.2% of women smoke during pregnancy. I should say have smoked. Okay, so that is confidence interval for categorical variable based on P tilde. Is that good? Okay. You have a few problems in there in your text dealing with that. There's a few problems where you have to kind of estimate how big of a sample you need. Okay, and it's just working backwards. You have if you want a certain margin of error, you set that as your limit, and you can solve for the n that you need. It's not too terrible. Just requires some algebra. Okay, actually, let's take a short break. We have a question.
1.96, the constant that we use